Hey everyone, welcome in this interview series where I will help you practice the interview questions on Node.js. In this series, I will provide you both the coding based and theoretical based questions to practice on your own, and I will provide you the both the solution and the detailed explanation so that the actual answer can become clear forever for you and you can easily master it and solve it whenever the similar questions comes before you. So without any delay, let's dive into it. So the first question is that we have to find out here the exact order of console.log outputs that would be printed in the terminal when it will be executed. Here the hint is that you have to clearly figure it out using the Node.js event loop phases. Uh, when you analyze it, then it would be easy for you to find out the actual answer. So you may take pause here and then later come out with your answer to check whether the actual output matches with your output or not. So the actual answer here is that the output would be in this sequence. The first console printed, then the sixth one, then fifth, fourth, second, and third. So, what was the reason of such a sequence? Let's now dig into it. The first and sixth console logs printed immediately because these were the synchronous commands and hence Node.js executed it immediately. The second and third was the callback functions and hence the second one was registered as a callback in the timers phase and the third one the immediate set immediate function registered as a callback in the check phase of the Node.js event loop phases and the promise function it was registered as a microtask in the promise jobs queue and the next tick one was actually also registered as a micro task in the next tick queue. Here, note that the next tick is holds higher priority than that of promise. Hence, the next tick would always print before the promise console log. Thus, these was the synchronous execution point of view to analyze this and later when the microtask queue processing occurs, since the next tick is of highest priority, next tick came before promise, and the timeout and immediate phases are part of the macrotask queues. Hence, event loop processes these phases in the order of timers phase, IO callbacks phase, idle and prepare phase and poll phase and check phase. So in these five phases, this set immediate executes in the check phase and the set timeout executes in the timers phase. Since the timers phase comes before that, hence the timeout console log printed uh, before than that of immediate. And since the immediate console log was the lowest priority among the other commands, that's why the immediate console log printed at the very last. So hence this was a critically based on the Node.js event loop phases. I hope your output may have matched with the actual output. If not, then I hope the explanation helped you to understand the exact idea behind this sequence. Next is that here you are provided with a code in which a user service has been provided that processes user requests, and over time memory usage by it grows indefinitely, and we have to identify that what is the exact issue here. So again, pause the video for a few seconds, and later I will help you explain this. So its actual solution is that each request creates a new event listener that was never removed, and event emitters hold references to all listeners, which actually prevents the garbage collection. That is the reason that memory is increasing linearly and it never decreases. That's why the memory is getting exhausted over the time and the program is getting crashed. To solve this issue, the code is to be modified a bit. The service.on function here, you have to use the service.once function, or the second option would be that uh, the request listener. For the second option, you have to explicitly remove the event listening after processing the corresponding event. For example, in this if block, here after the console.log, you can write the service.off function to manually switch off the event listening. Hence, these are the two ways to cope up with this problem and to not fall the prey for the uh, complete consumption of memory. So in this question, we are provided that the code of various modules like module a.js have this code: let count is equal to 0, and module.exports, and it exports the count and increment function that increments this count variable. Another is module b.js, which is importing the count and increment from the module A and executing the increment function and printing the value of count. And third one is the main.js file, which is also importing the module a.js, and from there it is extracting the count and increment function. And later on, the count from a constant is declared from the count variable which is existing in the module A. So again, main.js also executing the increment function, and there are console logs for the printing of count from A, and then again module B is imported and count value is printed. So we have to find out the exact values of the count and count from A so that we can arrive at a conclusion that what are the exact values of these console logs. So to figure it out, try to understand that the The count variable which is getting imported in the module b.js or main.js, it is part of the module a.js scope. And whenever any module is imported in in the Node.js code bases, the Node.js executes that file only once and it gets cached after that. So Node.js will only execute the content of the imported files whenever it actually imports that code. Otherwise, if it is cached, then the cached values will be served. So after that, we have to analyze the uh, increment function that was after it get executed, then what will become the value of count and what is actually the count from a. So understand that count from a will always gets the current value of the count which is existing in the module a.js, because count from a actually referencing to the count variable, while whatever we are exporting from the module via the module.exports, for example, the count variable here which is got imported, it actually exports through the copy by value method. But when the value is gotten read through this method, then it is actually getting the value via the copy by reference method. Thus, so when in the main.js, when the increment executed, it updated the value of count to 1 in the module a.js, but the count which was imported al already holds the value 0 because it came via the copy by value method. Hence, this console.log will print the value 0, and for this count from it is referencing to the count variable of module a.js, and now after the increment method execution, its value became 1. Hence, count from a became 1 now. That's why this second console log will print the value 1. And now module B is required here. In the module B, count and increment imported from the module A. Since at this point of execution, module A now has the count value is equal to 1. Hence, the increment when it gets executed on the count will become 2 in the module a.js, but it will not reflect in the module b.js when this console.log will be executed. Uh, at the time when this console.log gets executed, count will actually be holding the value 1. Hence, the here this console log will print the b count is equal to 1. And lastly, for the fourth console log final count, so since this is holding the value of the older count variable, which is actually the 0 value, hence this fourth console log will print the value 0. Thus, this is the solution here, and I already solved the this problem just before. Let's now dive to next question. So we have been provided a 4-core CPU, and your Node.js application is using the cluster module. If you will receive the 8 concurrent requests, you have to find out how are they distributed across workers and what are the implications. So to understand this, so here the catch is that master process by default uses the round robin strategy for the load balancing of the concurrent requests, and if the number of concurrent requests are greater than the number of CPU cores, all of the CPU cores will be processing uh, any particular request, uh, and hence at any point of time all of the CPU cores will be working, ensuring the better throughput. So for example, the requests 1 and 5 are processed by the worker 1, and 2 and 6 requests are processed by worker 2, and so on. So its implications are that uh, since all of the CPU cores are working at any point of time for the processing of requests, this ensures the better CPU utilization and throughput. And other than this, no shared memory is required between workers, hence eliminating the extra memory requirement. And each worker will be required the connection pooling for its own processing, which is a critical implication. It can be optimized via the external plugins. And lastly, the session storage must be externalized, because if it is not done, then the session will be erased because of the frequent context switching among the requests. Hence, these are the implications. This is a simple code base for the better illustration. So now let's try to solve this question. Here, the response from the database query is stored in the user variable declared as a constant. And then the set timeout is scheduled, which will execute these two lines after the 100 millisecond delay. A user's last access will be updated, and the response object will then be sent, and the response will be sent after the 100 millisecond delay. So suppose when the first request's set timeout is scheduled for the time period of 100 milliseconds, and within that period another request comes, and for that request the database query is executed and the response is retrieved, and the second request also uh, who that set timeout is also got scheduled, and after the time elapse of 100 milliseconds, the response of first request got successfully sent out via this res.end method, and when the second request's time 100 millisecond time elapses, it also tries to uh, send the response object, and hence the error will be thrown because within the small time period the same request object uh, may be overlapped with the more than one request object. Hence, the when the first request's response already got sent and second request response uh, get bound by the response object which is already sent via the request one. Hence, this program gets crashed with the error can't set headers after they are sent. Although this only occurs during the race conditions because it is evident that the request and response objects are request specific, means that the response object will actually be not shared among more than one request object, but during the async operations which are executing quickly due to the race conditions, uh, multiple requests may get bound with the same response object, which may cause the error like this. Hence, this is the reason that sometimes this code will fail with the can't set headers after they are sent. So its solution is that response must be sent before the set timeout is executed, because set timeout creates a race condition. Hence, to avoid this, response uh, must be moved out the logic or whichever causing the timeouts or another async operation. Let's jump on to the next question. In this question, we have to find out the this binding that with whom actually the this would be bind out, and what will actually be get printed when this log will be executed. Here, when the logger is defined as an object of logger class, and when the logger.delayed log method is called, then within the scope of delayed log, just before the execution of set timeout, the this will actually point out to the logger object. But when the set timeout registers the log method, so keep in mind that if the this is if the this keyword is referred to the some of the global objects, or via the this keyword if a uh, function is called under the strict mode, in both of these cases this keyword gets undefined value because of the because that's the actual mechanism in the Node.js. So when the set timeout registers the log method as a callback in the Node.js call stacks, and after the 100 millisecond delay, Node.js when finally executes the callback of log function. So Node.js executes that function under the strict mode. Hence, this actually then point out to the undefined. That's why in this question, these actually do not point to anything. It is undefined. So if we have to create its solution so that this must not be become undefined, and actually it should point to the logger object. Arrow functions can be utilized so that whenever the Node.js calls that function, arrow functions don't have their own this binding, and also they inherit this from the enclosing lexical scope. That's why the arrow method works in this case. The enclosing scope is the delayed log method actually, where the this keyword actually point out to an existing logger instance. If we don't have to use the arrow functions, we can take use of the bind method so that the actual instance could be binded to the callback, and hence the existing of the instance could be maintained. And third solution would be to use the store reference, like declaring a self constant which stores the reference to the disk, and then self dot log is executed so that the reference could be uh, passed down, which then actually help will help it to be solved. So our next question is that how does Node.js handle back pressure when it reads a large file, for example, a 10 GB file, and writing to a slow network connection along with it. And we also have to answer that what happens if back pressure is not properly managed. So its solution is that a back pressure occurs when data is produced faster than it can be consumed. In the streams, readable produces data faster than the writable can process it. Via the code snippet, this solution can be written down as follows. So in this code, write writable.write returns true if internal buffer is below the high watermark, and it returns false if buffer is full, which is actually the back pressure situation. Node.js by default provides the pipe method to handle the back pressure situations. The pipe method manages data flow from readable stream to writable stream, and it automatically pauses or resumes the data flow based on the back pressure situation. It also handles the error propagation, and also it closes the writable stream when readable stream ends. If back pressure is not properly managed, then we will obviously fall into the various error problems, like first one, that the memory will be easily exhausted. High memory usage leads to the garbage collection pressure, which escalates uh, as the usage of memory rises, and overall processing becomes slow due to the extensive memory swapping and potential application crashes with the JavaScript heap out of memory errors because of the extensive consumption of memory. So next question is, we have to find out here the execution order and also the reason that why such sequence actually came out. So let's figure it out. Here, firstly understand the synchronous execution phase. First of all, the console.log 5 before call will be printed because it is the first statement under the synchronous execution flow. After that, async task function is called, which is actually an async function. And under this, synchronous execution will execute until the first await keyword is encountered. So just before the encounter of await, the console.log start is executed. Hence, after this fifth console log, the as a second, this console.log will be printed, and the execution will forward to the promise constructor, which is created here, and it executes synchronously this console.log promise executor. So after the start, this will straight away be printed, and after this, the this set timeout is scheduled as a macro task for a 0 millisecond delay. Hence, after the second console log, the await pauses the function execution and returns the control to the caller of this async task function. Hence, after this second execution, it will caller is returned back to the main controller. Hence, after this, the seventh console log will be printed. So till now, our sequence became 5, 1, 2, and 7. Now, this was the macro task phase of execution. After this, uh, micro task will be happened, but since at this point of time, micro task queue is empty, hence no micro task is available yet to be processed. Now the timer's phase will be executed. Timer's phase executes the set timeout macro tasks. So uh, this set timeout is scheduled after the promise executor got printed. So this will be printed console.log timeout callback after this console log, because the set timeout is executed after this one under the timer's phase. Uh, After the printing, promise is resolved now, and now since the promise is resolved, this console log will be printed uh, without any delay. So after 3, fourth one will be printed, and since it got printed now, the microtask queue is now having this then callback. So this callback will be executed dot then, and under this callback, this console log is scheduled, which will be printed now. Hence, the order is 5, 1, 2, 7, 3, 4, 6. This is the actual order. So now let's dive into the next question. Would you use worker threads instead of the child processes for CPU intensive tasks, and what are the limitations of those? So worker threads are better when you are required to share the memory, and advantages of worker threads is that memory overhead is low because of the shared processes and no new V8 instances is required. Shared memory is provided via the shared array buffer, hence adding to the advantages of worker threads. And they are able to communicate efficiently with the transferable objects, and it's fast. Its startup is also very fast compared to processes because of the low memory requirements by them. And child processes are better when you need process isolation, and process isolation is required when you have security requirements as well. And child processes are allotted different memory segments uh, for the actual implementation of the isolation environments. And if one of the process crashes, another would be unaffected. Uh, Credit to the isolation. Since child processes require the individual memory segments, the resource limits also a concern there, because we can't have so many individual processes uh, because the memory is limited. Their limitations are that worker threads cannot use browser APIs, hence they are unable to access the DOM for the DOM updation or the reading the HTML elements from the DOM, and complex shared memory management as well. It is very hard to build the and manage the shared memory among the worker threads. Module limitations is also a contributing factor in the worker threads, because not every module is the thread safe. Hence, it becomes limited to utilize the all modules for the processing requirements via the worker threads. Often, uh, it comes to the point where the custom solutions need to be derived from the existing solutions just for the sake of addressing it via the worker threads. Our last question of this series is that we have to find out that how can we make this custom function work properly with the promisify function provided by the util module. So here the problem is that when the util.promisify is used, it do not returns all the arguments which is passed to the callback. It only returns the first argument from the callback, and rest of them it just forgets about it. So this would cause a serious problem. And another problem is that it do not maintains the this context when the promisify is used. So to solve this, the util.promisify offers a custom symbol accessible via the util.promisify.symbol, sorry, util.promisify.custom symbol. So with that, some snippet need to be added like this, custom async and under the square brackets util.promisify.custom, and then the data is passed as an argument to the callback, which is then registering a promise, and under the promise the resolve and rejection will be then processed. So with that method, all the arguments states which need to be passed through the callback will then be uh, properly maintained, and hence this problem will be solved out. There are multiple benefits of custom promisification. Among them are: first is the error transformation, which converts the string errors to the error objects, and another is the it formats the results consistently, which can be normalized as per the provided standards, and it handles functions that returns multiple values, and it also preserves the context and maintains the this binding correctly and smoothly. And in addition to this, it also add input validation before promisifying the function. I hope this series was useful to you. Write down in the comments that what next interview series that you would like to watch and understand. See you again in the next part of the video. Thank you so much for the watching.